Ladies and gentlemen, welcome to the show. The night shift decided to organize a forklift drag race, which had several consequences, including a completely misaligned stacker, which is symbolized by this drawing here, and the plane on which it is fixed is actually completely crooked and doesn't have any geometrical orthogonal relation with the base coordinate system of the robot, which is what actually happens more than often in industry. And about organizing forklift drag races, well, I have seen worse than that in my career. So the way to deal with the situation, the easy way, is the use of relativity. Relativity as defined by the AS language adopted and used to program F-series Kawasaki robotic controllers. Now, why say relativity? Because anybody in his right mind would teach a stacker in its own coordinate system and teach the origin and orientation of that coordinate system with respect to the base system of the robot. This way, when drag races during night shifts go bad, nothing bad has happened as soon as we clean a little bit the mess. So the question is how you define and how do you use a coordinate system on the F-series of Kawasaki robots. This is essentially a simplistic topic. All you need is one origin, one X position, and one Y position. With the following little remarks, you have to work pretty accurately, because the accuracy of your definition of your coordinate system will greatly depend and essentially depend on the accuracy of those points. Specifically, if the plane is inclined, you really have to go and kind of touch. See, here we have some flexibility. You have to take away all possible flexibility and really gently touch the base of your end positions. Now, this is important. So whenever you design a robotic application, always ask yourself, where can I go and hook to teach my referentials for different job sites? A job site being, for instance, a press, with respect to the next job site being the stacker where the parts are loaded and unloaded. So, enough talking. I took already time to define those positions as accurately as necessary for this example. So let me try to go by using K-terminal direct movements. Now when it works is spectacular, even more so spectacular when it fails. So let's try to concentrate and have the emergency stop always at hand. Whenever I hit the enter key on my keyboard, I'm sure to have my left hand firmly on the emergency stop switch. In case something goes bad, I would maybe have a chance to prevent a global crash. Obviously, it works better when we define a slower velocity. So let's start with this one, a conservative 10%. Yeah, and let's try to go and hit that point, land on that point, actually a little bit before that point. So we will use the following instruction, the name of the point, and I will put an offset 0, 0, minus 10 on X. Now, you have to understand that this kind of vector geometry works always on the two coordinates. So if this point is reached by the robot and the hand has a certain orientation in space in a certain position, the next operation will depart in the two coordinate system of that point. Now this is very important to understand. This portion is not operated anymore in the base coordinate system of the robo, where Z is vertical, X is toward you, Y maybe somewhere else. It operates in the two coordinate system of the hand at the present position just before this sign. That's very important to understand. And okay, maybe I'll make another video about the two reference show and how to use it and what it is really. But for the moment, let's assume that as frames, this is a known topic, so we just do a little refreshment. So let's see what gives. I'll try to do the start. And obviously my robot comes a little bit around. And the visibility may not be exactly as expected from the camera point of view, but this is just a check. So let's go and land completely. I always like to land on small steps. So I give 1 millimeter, which is already a good deal. And from this point onwards, I will retract once again. 10 millimeters. Because we will be moving on a plane which is not orthogonal or parallel or anything to the robot, just a plane randomly positioned in space. I will ask a little bit more distance, more clearance, right? And I will move to check my X position, the way it is defined. X, okay. Let's see what gives. 3, 2, 1, let's go. Finger on the trigger, finger on the emergency stop. There we go. Let's see if we can get a nice soft landing around there. Obviously we can. I can definitely even touch it by putting here a big fat 0 on the Z coordinate offset. Boom, I landed. So let's get lifted. Minus 20, even 30. Right? Fantastic. How sweet these machines are. You have no clue unless you really get to work on them. So we're going to move to the point Y, which should be done this way. So there we go. And we're going to perform a soft landing, hopefully. And even touch the board by putting a big fat 0 on the Z 2 axis offset. And that's it. We've touched. Fantastic. At this point, we have all data necessary to define our new frame, which is defined more or less as a point would be, because in fact a point is nothing else than a transform. So we define it as a point which is equal to a function frame which takes the following parameters. It takes the origin, it takes the X direction point, the Y direction point, and once again another point which will be used to specify the robot configuration, the wanted or the preferred robot configuration during operation in that specific frame. Left eye, right ear, wrist up, wrist down, and so on. So therefore we need another point which is just an example of how the joints need to be configured to operate in that frame. So let's go and hit enter and see what it gives. Yes, we have a point which is defined, and we may as well just use it. So first thing is to check it. So we would go there. Yeah. So what I will do, I will try to move to the base with a 30mm offset, backwards offset in my two coordinate system. This way I hope that they were not going to hit the boards, or at least not hit it too hard, in case things go wrong. And always the hand on the emergency stop, the other one presses enter. We have this. As you have seen, the orientation of the robot arm has changed. Now, what have we achieved? We have moved to the origin of our coordinate system. Let's go and check it. Try to make a soft landing. Maybe even touchdown. And there we are. However, the hand of the robot is oriented in a very different way than the one used to teach our positions. Now, the whole trick is, as I stated, is that we have defined a new point, which is called a PR base, and the particularity of this point is that when exactly on it, like we are now, our robot 2 coordinate system is exact match of our newly defined coordinate system. Therefore, if I am to move the robot in this direction using this axis, it will be exactly the same as if I move it in its own 2 coordinate system along the x-axis. Let's try to see if it is true. I will lift up a little bit because I don't want to scratch the board. There we go. Then I will perform an instruction which is called T-draw. This is a relative movement in X, Y, and Z with respect to the 2 coordinate system because it starts with a T. Do not confuse it with draw, which will do this with respect to the base coordinate system. So, X, 20, 0, 0. Let's see what it gives. Right, we departed. We can add a little bit more. And we are moving in the 2 coordinate system of the point PR base. So obviously, if I am to move back, I don't know if it's still in the IIT, it's still in the buffer. If I am to go back to my origin, PR base, I do the following thing, and I can even land. So how do you do relative movements inside? Well, there are several ways, but what I would like to show you is the essential way, and we will use exactly that. I will make a transformation here that once reached this position, we will depart in the hand, in the 2 coordinate system by 100 millimeters in the x-axis. So once again, double check everything. We have departing in the 2 coordinate system X. We will be flying at a height of about 5 millimeters. This should be good because we worked accurately, let's hope. Let's go and do it. And that's it. If I want to go on the y-axis, I will do the same thing on the y-axis as well. And it gives that. However, here my visibility starts to become poor because the robot hand is obstructing the camera. So I will do another small little EVO transform. And I'll have this. Now, please attention. What have I done? I went to PR base. From then on, I departed in the 2 coordinate system, which is actually our newly defined coordinate system, to 100 and 100 in X and Y, stood at a height of 5 millimeters with respect to the 2 coordinate system. And once I am there, I tilted my 2 on its x-axis by minus 20 degrees. Now, can I move like that? For sure I can. Let's go and hit our X position, our origin first. Always check twice. Always check twice. So, there we go. Can I land on my 2 coordinate position? Yes, because I defined my 2, and my 2 is quite accurately defined. So, sorry, minus 20. I said minus 20. And I will land. Can I land? Let's see. Okay, I did land. Can I lift off? Yes, I can, hopefully. Can I go, for instance, on the X point? Let's check it out. The X point, however, is not yet defined into that coordinate system. So I may try as well to go and approximate it. X, maybe around here. Double check. Let's go. Yo, kind of close. Well, let's not be maniacs for this demonstration. Try to see if we land correctly. And yes, we do land. We can do even a little bit more magic. On this point, I will just lift myself a little bit in case I touch. 1 millimeter should be sufficient. Yeah, and I'll go back to my original position of the arm. And because the 2 is defined, and we defined all the points with the tip of my 2, we will have that. How cool it is. Really. Let's go and do it once again. And because we are not only limited to one transform after what happens, I can also try to make a rotation of 45 degrees. Hopefully I will not hit a singularity with my wrist. And exactly that's how it goes. We can even be a little bit more generous. Right? Or even so. So as you can see, the frames, remote frame definition in Kawasaki robots allows a huge variety of very interesting approaches and very interesting movements. And this is why I invite you to use it, learn how to use it, practice and use it. So that's about all I have for you today. And should you have questions, well, comment down. Don't forget eventually to subscribe if this channel is of any interest to you, because we are bound to produce more videos with more interesting cases. I guess the next one will be the demystification of the 2 coordinate system, which is kind of shaded in mystery. And I would like to make it clear as possible for everybody, because this is a lifesaver and an absolute must in 6-axis programming. So out of the 2 essential things, coordinate systems and 2 coordinates, we just cleared 50%. 50% of the mystery is left. So in about 1 more video, we'll be ready to jump and program these beautiful babies, right? All right. Take care of yourself. Thanks for watching. Subscribe, like, and comment in case you feel the need. Bye-bye.